Hello, everybody. Welcome to our RAG Hack live streams.
RAG Hack is a free global hackathon happening from September 3rd to 16th. RAG is a technique to get a large language model to answer questions based off your data. We have more than 25 live streams teaching you how to build RAG apps with different Microsoft technologies, plus 10 cash prizes for the best RAG apps in each category. So we're super excited to have you join us for this RAG Hack. And now a word from our friends at Reactor.
Hello, everyone, and thank you for joining us for today's session. My name is Askia, and I'm one of the event planners for the Redmond Reactor space. Before we get started today, I've got a few things to go over. So if you could please take a moment and read our code of conduct. Basically, what it says is that we're seeking to provide a respectful environment for both our audience and presenters. We encourage engagement in the chat, but please be mindful of your commentary, remain professional and on topic. Useful links will be shared throughout the chat, so keep an eye out for that. And the session is going to be recorded and will be available on demand in 24 to 48 hours on the Microsoft Reactor YouTube channel. And that brings us to today's session. It's going to run approximately 1 hour with time for questions throughout. And with that said, I will now turn it over to our speaker.
Hello, everyone. So I'm Cedric Vidal. I'm a principal advocate at Microsoft, and I'm going to talk to you today about a way to improve the performance of your RAG setups with a method called RAFT. It stands for Retrieval Augmented Fine-Tuning, and let's jump right into it. So first of all, the way I'm going to organize this presentation is first I'm going to present the basic concepts such as what is RAG, what is RAFT, and then I'm going to do a run through of a repository that I've prepared that you can use to apply the method to your projects and walk you through the code and how to use it. But first, RAG. So I'm sure you're all familiar with RAG, but real quick. So the principle is that you ask a question to the system, to RAG setup. And in order to ground the results and give a domain-specific answer, you search for documents in some kind of data store using some kind of vector similarity search. You retrieve the documents that are the closest to the to your question. You bring them into the context, and then you build a new prompt that you send to the LLM, which contains both the question plus the document, the parts of the documents that are relevant, in order for the LLM to generate a grounded answer. So that's basically how RAG works. The problem with RAG is that sometimes it can be the answers can be frustrating because the documents that are retrieved from the database may be irrelevant. So because the way the documents are looked up is based on vector similarity search, and you might have a document that while close to your question from a vector embedding standpoint, from an embedding standpoint, is actually not really relevant to answer the question. It actually adds noise and drives the attention of the model away from what matters. So different ways to improve the situation. One way to improve the situation is using that method called RAFT, which uses documents from your domain knowledge to fine-tune a model optimized for your use case. But what is fine-tuning? What does it mean? So it refers to customizing a pre-trained model. So basically, when you think about GPT 3.5, Turbo, GPT-4, Llama, or those kinds of models, those have been pre-trained on a huge quantity of data from the internet. That data, so those models are extremely powerful, and they are usually very big, and they know a lot of things. But when it comes to your own domain, when you are an enterprise or you want to build a product or an app, usually you have your own domain expertise. You have, for example, if you work for law in the law industry, or in healthcare, or in gaming, or whatever industry specifics you work in. Those very big models might have an idea, a general idea of the industry and general idea of the domain, but might not have the very specifics that you own. So what you want to do is use the data specific to your domain and train the LLM to be better at answering questions on that domain. That's where fine-tuning comes in. The principle is you take a pre-trained LLM, such as GPT-3.5 or a small llama model, 8B, and you take a data set and you combine the two, and you create a fine-tuned version of the LLM that knows about your domain. Why would you be doing that? There are multiple reasons. I mentioned domain adaptation, I mentioned domain specificity, but it's not the only reason. Another reason is performance. Very big LLMs, as powerful as they may be a bit slow or costly to run. So when you fine-tune on a smaller model, because it's smaller, it's going to be faster to execute. And it's going to be cheaper. The cost to run the model is going to be lower because the number of parameters is going to be smaller. It's going to consume less memory, less GPUs. It's going to take less time to execute. So usually it's going to cost less money. And it's gonna, the last reason why you might want to do that is differentiation, because being specific to your domain, your industry, and having been trained on your proprietary private information, you can create an edge compared to your competitors. And sometimes that edge makes a whole difference, and can be the difference between users wanting to use one company or using another. And because we are at the beginning of the AI race, we are at a time where differences between companies are very, very important. And the faster you go and the more you fine-tune your model to be specific, the more your users are going to be incentivized to come to you and use your product. But it's very challenging. Fine-tuning is complicated. First of all, you need data. And the thing is, it's not just data as any kind of data. Because most companies, most enterprises have data. They have their documents, they have their knowledge expertise in the form of Word document, PDF documents, or structured databases. But in order to train an LLM, it's not just you take a database or you take a bunch of Word documents or PDF documents and you tell the LLM, hey, just learn about it. It doesn't work that way. You need to provide a curated data set prepared in a way that is tailored to the task at hand. So for example, in like most RAG systems, the goal is to be able to ask a question and get an answer. So it's what we call a Q&A type of task. So you need to prepare a data set with questions and answers about your domain. And that's where usually it becomes difficult, because you might have a ton of documents, but you usually don't have it formed as a set of questions and answers. Second is compute. It's very hard to come by GPUs nowadays. It's very costly, it's scarce, hard to get. The third one is expertise. It's it's still a complex subject. Coming up with the people that know how to train those models, how to prepare the data, those people are hard to find until now. So a few recap of different domain adaptation techniques. FSL is basically in-context learning. It's basically when you give a system prompt, everybody has done it at this point, most likely. When you have GPT or Llama and you give instructions so that the model is going to follow. Then you have RAG, Retrieval Augmented Generation, with the limitations that I mentioned, is that usually some documents are going to be retrieved that actually are noise and not relevant to answer. Then you have fine-tuning. Where are we at? So all of those approaches I just mentioned have pros and cons. In-context learning is super easy, but only goes so far. Fine-tuning is very efficient, but does not allow, it's limited in, you need to fine-tune, which is very expensive every time you want to add new knowledge. And RAG comes with the irrelevant documents that I mentioned. So UC Berkeley came up with a method called RAFT that provides an answer to all those previous answers and provides a new approach that combines fine-tuning and RAG together. Let's see how it works. So the principle of RAFT is like a student passing an exam. It's either closed book or open book. When it's closed book, it means that it's basically fine-tuning. It's you have worked for weeks and months or a year to prepare for an exam, and you arrive the day of the exam and you don't have access to anything, no books, no internet, no nothing. You do the exam only from memory, only from what you have learned. This is fine-tuning. And you might hallucinate, like even as a student, you might be, you might misremember something, you might forget something, you might confuse something. On the opposite, open book is when, okay, you might have studied, you might have prepared the exam, of course, but when you arrived at the exam, mostly you have a pile of books in front of you, you have all the knowledge, but you don't know in which book the information is, because those books are handed to you at the start of the exam and you had not seen them before. So even if you have all the information required in order to answer the questions and pass the exam, you don't know in which book to look. So it's going to take some time to go through all the first pages and to find where the information is. And when you look at the titles of the sections, you might find red herrings. You might think that one part of the book is actually relevant. You'd spend time reading it, and then at the end, it's not. So that's RAG. So RAFT is basically building your own librarian. It's basically going to the library where the librarian knows about all the books, and you can ask him a question, and he knows, because he has read all the books, he knows which books are relevant to answer the questions, and he can direct you to those books and answer your questions. Real quick, an example using vampires, a vampire domain. So what I did is that I took and you know what? Actually, I'm going to switch to the demo now and use an actual, a different domain. I'm going to use surfing for my example, but I'm going to switch to real code now. We don't need the slides anymore. You're going to have the slides, so you can still go look at the slides, but I'm going to switch to the demo. So the RAFT distillation recipe repository that I'm showing here, actually, you have on the very last slide, you have a link here, a QR code, and you have an aka.ms link, so /raft-recipe. And when you enter that link, you're going to be redirected to the Git repository that I'm going to show you now. By the way, let me go to the set repository, aka RAFT recipe. So this is the GitHub repository that implements, it doesn't implement. RAFT is implemented by UC Berkeley. So there is another aka.ms link for RAFT repo. So this is the RAFT repository, which was created by UC Berkeley researchers. And the RAFT decision recipe here packages it in a way that is super easy to use on Azure AI. So it contains infrastructure as code to provision everything you need to spin up all the resources on Azure AI to run the notebooks. And it contains 4 notebooks, one for each step of the RAFT process. The first one is synthetic data generation. The second one is fine-tuning, then deployment of the fine-tuned model, and then finally evaluation of the fine-tuned model. So I have already checked out the repository. Oh, by the way, I recommend using Codespaces. There is a link here that you can click, which is going to open the project in a GitHub Codespaces. The Codespace is pre-built, so it should be pretty fast to get up and running. Let me switch to my Codespace here, where everything is already loaded. And let me show you the first notebook, the synthetic dataset generation notebook. So I mentioned the closed book and open book. I mentioned RAFT. Here's another diagram that is interesting. So I'm going to walk you through that process. So the principle of RAFT is that it takes documents from your domain knowledge. So for example, a set of Word documents or a set of PDFs, and splits them into small chunks, indexes them, and for each of those chunks, is going to use a big LLM. So you can use your multiple LLMs. Right now, the repository is set up for Llama 3.15 405B, but soon we're going to add support for GPT-4. But for now, only Llama 3.1 405B. So for each of those chunks, it's going to generate a few things. It's going to generate multiple questions. And for each of those questions, it's going to generate an answer and a chain of thoughts. The chain of thoughts is basically the steps, the thread of reasoning that leads to the answer. That the chain of thought has its own paper, and that's a paper that came up with that method that dramatically improves the quality of the answers. So RAFT leverages chain of thoughts. In addition to the answer and chain of thought, for each of those questions, we are including some oracle chunks and distractor chunks. The reason why we're doing that is to teach the model to learn to pay attention to what matters. By including distractor chunks, so chunks that are actually irrelevant to answer the question, the LLM learns how to ignore those and pay attention to what matters. Then after we have generated that big list of questions, answers, chain of thoughts with their oracle and distractor chunks, we are going to split that data set into 3 splits: the training split, the validation split, and the evaluation split. Before I get into the details of explaining what those are, let me run the RAFT command line. Let me go through the notebook here. So first of all, the first step is to set up the RAFT repository, because the RAFT repository is a UC Berkeley project, and they don't have a Python library that you can pip install, sadly, yet. So in order to work around that limitation, The setup underscore raft.sh script here is going to check out the project locally here, and in a location where the CLIs are going to be available, and the notebook is going to be able to invoke them directly. And then there is, so before you can run all of this, so the infrastructure is available as code with a tool called AZD. So you can just do AZD up. I mean, you first need to do AZD auth login, which I have done already, so I'm not going to do it again. Then you can do AZD up, which is going to provision the infrastructure, and same. I've done it already, so I'm not going to do it again. And what's interesting here is that you also have infrastructure, a suite of infrastructure tests that verifies, and I can run it again here, that verifies that everything is running as expected, that all the endpoints are available and can be used by the scripts. And what's happening? Let me run that in the command line to make sure that everything is working. Yes, it is working. So maybe it's just my notebook. What's going on with my notebook? Okay, I'm going to restart the kernel. I'm going to execute. Here, I don't need to execute that. Let's go. Okay, I have a problem with my setup here. I'm not sure what's going on. So luckily, I had executed my notebook before. Okay, so I'm not sure what's going on. Anyway, it's okay. Can I execute that? Yes. So why it is not running? Okay, I'm not sure what's going on. Oh, interrupt. If I interrupt this, okay. It seems that I have a technical problem with my notebook. Let me, in the back, I'm going to open in the web version of CodeSpace, just in case it's a problem with my VS Code. Okay, I don't have, okay, technical difficulties during a live. It's great. Anyway, I'm gonna skip this. So as you can see, it works on the command line. I have a problem with my notebook for whatever reason. So I'm going to ignore that and just walk through the steps. So here, after you have verified that everything in the infrastructure is set up correctly, all the endpoints are deployed correctly, the notebook is going to show to you, you're going to select which data set. I'm sorry for the scrolling. I was looking for where I was. So the repository comes with a few samples. So here in the sample data directory, you have 4 domains. One about surfing, one about vampires, one about Dune, the movie, one about bats. So I used to use the vampires dataset as default, but believe it or not, talking about vampires was yielding some pretty awkward questions, which did not pass the safety mechanisms of Azure. So I switched to surfing, where it's less controversial and there is no such risk of violating those filters. So here we go, surfing. But you can, at home, try with any one of the other domains or documents. Here I use a single PDF for sake of speed, but you can point at a full directory. You can also upload, and it's highly encouraged, to add to the repository your own folder with your own PDFs. If you have Word documents, convert them to PDF first. Then here, so you specify the data sets, the documents that we are going to load, to analyze. Then here we're displaying the document. So as you can see, it's a PDF about surfing. And as you can see, that PDF does not contain any questions and answers, so to speak. It's just a document that explains what surfing is, talks about the history, the key people in the sport, the different types. You see stand-up paddling, longboarding, shortboarding, what a personal watercraft is, whatever. So a few different things about the domain of surfing. Then you have the RAFT Python. The RAFT Python script, which is the main code that is going to read those documents of the domain and transform them into a data set of questions and answers. This takes some time. For just one small document, it takes roughly 2 minutes. But for bigger data sets, for example, for the talk I gave earlier this year at Build, it took 2 days for, I believe, if I remember correctly, something like 10,000 Q&As. So it can be a pretty lengthy process. So be prepared for that. The cost to run this notebook with the default small data sets is roughly, it's less than $5. It's very cheap. For a bigger data set, like for the build talk preparation, it costs between $100 and $130, if I remember correctly. So it's still pretty reasonable to fine-tune your own domain on a pretty sizable data set.
So yeah, Cedric, we're getting a lot of questions about pricing in the chat. So I shared that on the repo you do have the cost estimate section, and people are just trying to reason about, like, if we've got this many pages, what's going to be the cost, and then also what's the cost for inferencing. So I was just trying to log into AI Studio to see what the costs are, because those costs vary depending on which model you fine tune, right?
Yes, and also the specificity of running. There is a difference in the cost structure between running a normal pre-trained model, such as Llama 3.1 and 8B, and running a fine-tuned model. Because running a fine-tuned model, the Azure AI platform does fine-tuning using a technique called LoRa, which is very efficient. That's why fine-tuning using Azure AI is so cheap, because $150 or $130, like ish, to generate a data set, fine-tune a model is very, very cheap compared to the millions of dollars required to create your own pre-trained model. So this is very cheap, and the way this is achieved is using LoRa for low order ranking algorithm. But the thing is, to run LoRa in production is quite tricky, and you need to have servers to hold the LoRa layers, as well as the base layers, and stitch them together dynamically. So there is infrastructure cost related to that, which is why when you deploy a LoRa fine-tuned model, there is there is an hourly price in addition to the price per token. So you have two things. Whereas when you deploy a pre-trained model, you only pay by the token, serverless.
Okay.
Yes, does that? But I'm sorry, I don't have actually I do. I think I have a slide here on pricing. I may have the answer to that question. Do I? Yes, I do. I have a slide for that. So here's the cost structure. Like I said, the cost of the dataset generation plus fine-tuning cost, 80 plus 50. So $130-ish. Inference is different. Like I said, there is, and I forgot, I didn't include the, okay, I'm forgetting here. I'm sure there is a cost I'm sure there is a cost per hour for fine-tune model, which is not appearing here, and I apologize. But for the price per 1,000 tokens, for output tokens, it's 0.01134. And at the time of writing that slide, so the price may have changed in the meantime. So it would be safer to go look at, and actually, let me see if I have the price on hand. Can I see the actual price here? Let me bring a window here. AI. Did I have AI Studio open already here? Yes, I do. So actually, I may be able. Do we have a fine-tune model? Thing is, I don't have a new one here. So, but the price may appear. The price for fine-tune may appear even. Let me see. Serverless pressing enter. Yes. That's what I thought. Okay, so here you have the full price structure. So fine-tuned. Okay, so as you can see, and the price has changed actually since I did it go. Yeah, it actually went down. That's great. It's less expensive. For input tokens, it's $0.0003 per 1,000 tokens. For outputs, it's 0.000061. And there is a hosting cost, like I mentioned for LoRa, which is 0.74 per hour. So it's not very expensive.
Is that cost, this was another question, will that hourly cost just start accruing as soon as it's up? So basically, like as soon as your model is done, you're paying the hourly cost, or can you like pause it?
That's a very good question. It automatically pauses. So yeah, no, it's great. No, it's a very, very, very cost-efficient solution. Really, in my opinion, serverless is a game changer. I mean, it's a very, very, very cost-efficient way to deploy fine-tuned model and model in general. So the way it works is that as soon as you use it, the LoRa servers are gonna stay up for an hour. But when you stop using them, after an hour, they're gonna be taken down. So it's not by the minute; it's still by the hour. But given that it only costs $0.74, so it's not the end of the world. It's pretty cheap still. But after an hour, it's going to be taken down, and you're not going to pay for it. So it's very, very good. Like for example, if you even for development, like when you use the server only occasionally, and you have the code standing still and not using it for some time, it's perfectly fine.
That's great. Yeah, I didn't realize that the hourly cost was like that. There's another question. There's lots of questions actually. Can you download the fine-tuned model for running locally?
No, you can't. No. So there is a reason for that. It's actually, so there are some pros and cons, obviously. So using a platform such as Azure AI serverless is awesome for the reason we just mentioned. It's super cheap. It's super easy. Like I'm going to show to you how easy it is. Like it literally, all the infrastructure, you have nothing to care about. Everything is done for you. And it's also from like a license standpoint is also very interesting, because when you use Azure AI to fine-tune a model, you can use the fine-tune model for commercial purposes. You can. Whereas when you download the weights and you do the fine-tuning yourself on your own GPU, there are some restrictions depending on the model. And so for like enterprise use cases, Azure AI offers better licensing, generally speaking. Of course, I invite you to look into the specifics to be sure you understand how everything works, but it's a good solution for enterprise use cases.
Nice. Okay, so getting back to your repo, there was a question about the generation step. Was how does it come up with those questions?
Oh, excellent question. So let me go back to my diagram. Oh, No, actually, I'm gonna use a slide that actually I skipped. No, do I have a better? Okay, let me use. Sorry, I'm trying to find the best way to answer that question. Let me show sample data. So here is an example of the generated data set. So the way it works is it's gonna take a chunk. So here, here's a chunk. So sorry, it's because it's in a list, it only displays the beginning. But let's say that we are, sorry, I'm finding my words. Let's say that we are looking at that paragraph. It's gonna take that paragraph, look at what's in it, and say, for example, the term surfing refers to a person riding a wave using a board. So we're going to ask a big LLM such as Llama 3.145B, hey, here's a paragraph, come up with a list of 1, 2, 3, or 4, it's configurable, there's a parameter for that, come up with a list of questions about that paragraph. So it could be, what does the term surfing refer to? So basically it turns the knowledge, the facts around and invents questions about those facts. And what's very, very interesting is that it leverages a property of those large language models for which they are very good at, which is imagining things, like coming up with things where usually it's a problem. Like when you don't want, when you query a model, you don't want it to give you answers that are wrong, that do not exist. But when it comes to generating questions, on the contrary, it's a very good property to be able to generate things. And what's interesting is that, so you use that property to generate the questions, and then you use the other property, which is instruction following and grounding, when it comes to generating the answers. So you use a different capability of the big model. So at that step, let me go change again to, oh my God, I'm skipping through this is very bad. Sorry for the scrolling. I hope it's not too dizzy. After you came up with a question using that capability to imagine things, you're going to ask the model to generate an answer, which requires to be precise and correct. But this time, you ground the question with the oracle chunk from which the question was generated. And you ask specifically the model, follow the instructions, like ground your answer into that oracle chunk. And by the way, after, you can also evaluate and verify that those answers are grounded using a different LLM. And this is what's included in the evaluation notebook, the last notebook. And I don't think we're going to have the time to look into, I mean, we might, I'm not sure, but that's a different topic. But yes, that's how the questions are generated. And the chain of thought also is a very interesting property, because by asking the model to generate the answers by using chain of thought and asking it to go step by step, that's how you maximize the chances of, so it doesn't eliminate hallucinations, but it maximizes the chances that your answer is going to be correct. And if I open, I'm pretty sure, sorry, I should have, no, it's not very convenient. Let me look at the dataset here and the generated files. So here are the generated files. If I take the train, and I'm going to take the first one, I'm going to create a new document and sample.json, and I'm going to format it. Format document, yes. So it should be easier to explain. So here is the generated question. Here is the oracle context. And can I display and go back? What wrap? Yes, awesome. So here's here's the oracle context. It is held in high estimation and very old after use, and Okay, I'm not sure what that is. When Mark Twain visited Hawaii in 1866, he wrote blah, blah, blah. Okay, so here's the oracle context. And here, let's look at the question which was generated. What was the national pastime Mark Twain observed in Hawaii in 1866? Well, actually, we're lucky because that's literally what I was looking for in here. So he wrote, I mean, if I search for Luke, so I was looking for Luke in the oracle context, but actually I stumbled upon a different thing, which is the chain of thought that I was mentioning. So what's interesting is that the chain of thought answer says, to answer the question, we need to identify the national pastime Mark Twain observed in Hawaii in 1866, and it goes step by step. The context provided gives us the necessary blah, blah, blah. We look for the part of the context that directly mentions Mark Twain's visit to Hawaii. We find it in the sentence, Mark Twain visited Hawaii. He wrote, in one place we came upon a large company, blah, blah, blah. End quote. From this sentence, we understand that Mark Twain observed the specific activity that was considered a national pastime in Hawaii in 1866. The activity is explicitly mentioned, surf bathing. And the final answer is surf bathing. So that's how it works. Step by step, using the oracle context, it gives you an explanation, step by step, how it goes about generating the answer. And finally, it extracts the key piece of information and puts it after the answer token. And that's what we are going to fine-tune the smaller model on. And what's also very interesting is that by fine-tuning using the chain of thought, because the whole thing here is going to be used in the answer for fine-tuning, is that it links somehow, it links the question to that answer with everything in between, with the chain of thought, with reasoning. So it teaches the model not only what the answer is, but why that's the answer. So it really teaches your model to become an expert at your domain. And of course, when you look at such a public data set, most large language models pre-trained on the internet know about surfing. I mean, let's be honest. But this is because, for the sake of that open source public repository, we need to use public data sets. But the principle is that when you're going to use the RAFT methodology on your own enterprise proprietary data set, you're going to give it information that is not public. And that's how you're going to train the model to learn. You're going to teach the model about something that is not public, that only your company knows. Sorry, that was a very long answer.
No, it was a great explanation. I love all the questions. We do have one more question. I know we're taking up a lot of time, but these are great questions. So when you're doing this generation stage, I presume it's using our like GPT-4 it's a GPT-4, right? That it's using to generate these answers. So you're
right now it's Llama 3.1 405B.
Oh, okay. 405B. Okay. So you're using a large model. Yeah. So it's a large model. So you're using a large model. So how do you avoid the like rate limits? Like what sort of TPM, tokens per minute capacity do you need on that large model when you're doing this massive generation?
Okay. So that's an excellent question. So to be honest, when we were preparing the build talk earlier this year, we ran into issues because we ran a pretty massive dataset generation job. Like I said, we generated a bit more than 10,000 data points. So we did run into TPM limits. So first of all, the code base has, oh, by the way, because our generation was so massive, we literally went through all the problems you can imagine with the UC Berkeley RAFT code base. And we did so many PRs on their code base to make their code way more robust. So as part of that work, the code now does automatic retries, like catches issues. So it's robust. Like if it hits a TPM limit, it's gonna wait and apply exponential backup and retry later on. That's one part of the answer. But the other part of the answer is that, okay, it's good. The code is robust. The code is gonna, wait and retry when the TPM limit is back. I mean, when you have TPM availability again. But still, you might face a situation where it's annoying, like you want to go faster. So what you can do is there is an amazing open source project that allows to load balance across multiple endpoints. And the name of the open source project, obviously I'm blanking right now. I think I mentioned it somewhere. Yes, okay. I'm saved. I wrote it down. So it's called Light LLM, and that small piece of software is amazing. And I was previously working at Microsoft in the Microsoft for Startups team, and I was working in a partnership with like Y Combinator startup, and that startup was part of the last batch. And they develop an open source, OpenAI compatible proxy that allows you to do load balancing across many kinds of LLMs. So what you can do is install that, and that's what I used for the build talk. I spin up, I think from memory, I spun, I think I wrote it down. Yeah, I had one mass endpoint and two map endpoint. So to be honest, the map endpoint are pretty expensive. This is high end, A or H, I forgot. Yeah, A100 GPUs. Each of those has like eight A100. So this is a very, very big setup. And I had two of those thanks to my colleagues in the product teams. And so I had done a load balancing between those map endpoints and that mass endpoint. Mass stands for model as a service, and that's what the notebook here is using, which is very, very cheap. Map is different. You don't pay by the token, you pay for the infrastructure, you pay for even when you don't use, and it's more expensive, but it's low latency. So depending on your use case, it might be interesting. It's harder to set up because you need to provision it, manage it, think about taking them down when you're done with it. But in that case, yeah, I was using a mix in order to maximize my throughput. And by using those three, I was getting 350 tokens per second. So here's the answer to the question.
All right, thank you. That's great.
How much time do we have more?
Well, you have 12 minutes left.
12 minutes left. Okay. So, okay, awesome. Shall I continue, or do we have more questions?
Yeah, keep going.
Okay. So, I forgot where I was, but so I was going through. We had I had finished showing how the generation process is, I think, or I was going through. Yeah. Oh, actually, I had done everything in my notebook. Actually, I forget. So let's look at the sample. I had done it. So as you can see here, so when you run the when you run the RAFT.py script, here it goes. So it takes some time. At the end, it's going to generate the dataset. Then the notebook is going to walk you through reformatting the files into simpler formats that are more suitable, that are suitable for like working with, simpler, and also suitable to upload to the serverless fine-tuning API. And here I was showing you the table, but what's more interesting is that here I actually look at a specific Oracle context and the specific question that is generated. So as you can see here, the question is, what island in Hawaii is known for having some of the best waves in the world? I think it's Maui. I'm not sure. Oahu, maybe. Okay, apparently it's Oahu. I did not know. So you have the chain of thought, but I'm gonna skip it quickly because I mentioned it before. And then you have the instructions that is like assembled, which is going to be used for fine-tuning, which contains the list of documents as well as the question. Then we do the splitting into training, validation, and evaluation, like I said. But let me explain what those are. So the training split, by the way, this is not specific to RAFT. The splitting a data set between those three splits is standard machine learning. The principle is that the training split is used to update the weights of the model. That's how you teach the model new knowledge. The validation split is not used to update the weights, but it's used during training to measure whether we are improving the quality of the model or, on the contrary, if we are diverging. So the validation split also is very important because that's what drives the model in the right direction. The evaluation split is kept aside. It is not used at all during training. It is used after the final fine-tuned model has been produced to evaluate it. So the evaluation split here, in the context of that notebook, is going to be used only in the last notebook, the evaluation notebook. We export the different splits in the proper format. So basically, that's where that notebook ends. Once you're done with that notebook, you have all the files that have been generated into the dataset directory in the dash files subdirectory. You have all the formats. So HF is the internal RAFT format. FT is the format optimized for Azure AI fine-tuning. Then you have the second notebook. I don't think I'm going to have the time to go through all of them, but very quickly. By the way, all of this is infrastructure as code. It doesn't require, you can do all of this through the UI, except for RAFT, but fine-tuning deployment can be done through the AI Studio UI. But here, the goal of that notebook, and by the way, I believe this is the only notebook that provides you with a complete end-to-end demonstration of how to do data gen, fine-tuning, deployment, and evaluation fully as code first. So here it shows you how to fine-tune and to start a fine-tuning job. And okay, I'm gonna skim through it very quickly. At the end, what matters is what at the very, very, very end. Here, you submit the fine-tuning job, and you can, when you click on the link here, I opened the link already, and I opened it here. So what's very interesting here, and the fine-tuning job completed. I started it at the beginning of the talk. And you can see a visual representation inside ML Studio. You don't have to look at it if you don't want to, but I like to look at it because I like to see what's going on under the hood. So when you click on that link, you have the possibility to navigate in different components of the fine-tuning pipeline and look at every block and see how it's working. And after it's finished, the model is going to be available in the deployment section in AI Studio and ML Studio as well. And sorry, not in the deployment, but in the fine-tuning section here. Yes. So here we have our fine-tuned model, which is the result of the fine-tuning job. And so after you're done with fine-tuning, you can go to the deployment notebook, and same, code first, everything is automated. You just go through the cells, and it's going to deploy. And actually, you know what? I can, if my notebook issue is resolved, which it looks like it is. Yes. So I'm going to go through those. So here I am waiting for, okay, I have a problem here because it doesn't find the model which was fine-tuned when it should have fine-tuned model name. Why isn't it D1, D3? Oh, looks like I have a bug. Okay. Okay, I have a bug, it seems, that I will need to fix. So I'm going to interrupt. I'm going to restart. And I'm going to run all to go faster. And hopefully this time it finds the... No, it does not. D3 CB. Why isn't it finding my model? That is strange. Okay, I'm gonna have to troubleshoot that. This is not expected. Anyway, when it's working, it's going to, and you know what? I'm gonna try to deploy to run the model. Wait for model. Yeah, no, okay, it's not gonna work. Okay, I'm gonna have to fix that. But so that notebook is going to deploy that model, and what I can do is do it manually. So here, so this does manually what the notebook does programmatically. So once this is done, you're going to have an endpoint, a serverless endpoint of your fine-tuned model that you are going to be able to consume as any other model. And so the key takeaway here is that once I have fixed that bug, that recipe here is really an end-to-end solution that allows you to super easily fine-tune your own model using your own document. You have nothing to do. Like, you just provide the documents, which usually you have. And it generates the data sets automatically. It does the fine-tuning automatically. It even evaluates the quality of the model. All you have to do is provide the document and be patient. And at the end, you have your own model.
So Cedric, we had a couple questions. Can you fine-tune a fine-tuned model? Is that even a thing?
So that is a good question. So not using, in theory, yes. In practice, not so much. Because when you think about it, a pre-trained model is a model that has been fine-tuned already. Because a pre-trained model, like a model that you use, such as Llama 3.18b or GPT-3.5 Turbo, those models have not been created in one go. Like, first you had pre-training, then you have like 2 or 3, I forgot, follow-up steps to fine-tune the models to apply RLHF, reinforcement learning using human feedback, or other kinds of alignment techniques. Those are fine-tuning techniques, approaches, like variations. So when we do fine-tuning, like when we talk about fine-tuning here, it's about fine-tuning a pre-trained model using your own data. But yeah, in theory, you could fine-tune it again. Just on Azure AI, it's not going to be practically possible, because fine-tuning is about creating a LoRa layer, and it doesn't make much sense to update the LoRa layer again. So yeah.
Okay, and then another question. So, we have that generation step. Once we've done that generation step, we can, in theory, use that generated data for multiple fine-tuning models, right? Like, if we wanted to try fine-tuning 7B, 70B, etc.
Yeah. So the model comes. So first of all, here at the top, in the fine-tuning notebook, you can select which model you want to fine-tune. So if you go towards the top, if you search for parameter, yes, here you have the possibility to modify the base model that you want to fine-tune. And if you look at the parameters directory here, you have 3 predefined configurations that you can look at. The 3.18b is the default one, and you have values for each parameters. And you can update manually the value here. Just make sure that it's consistent with what's in the file here, because those values have been tested and they are known to work. All the files here are known to work. Also, what you can do is there is a command line script here, run all.sh, which allows you to pass. Yes, here. It allows you to. So it uses a framework called Papermill, which allows to do parameter value replacement. So basically, you point Papermill at one of those parameter YAML files, and it's going to variabilize the run and use the values inside. So basically, it's going to be able to, you're going to be able to run all the notebooks and switch from 3.18b to 3.8b or a different version. And we are currently working on adding support for more models. So in the upcoming days and weeks, you're going to have GPT 3.5, you're going to have Microsoft 5.3. Those kinds of models are going to appear in that folder. And the syntax to select which parameter file is -p. So you say run all.sh -p, and you point at the YAML file. And also, you are welcome to submit PRs on the repository. If you try yourself a different combination which works, feel free to submit a PR.
Sweet. All right. So we are at time. I don't know if you have to jump to something now, because there are, of course, more questions.
Yeah, no, I still I think I have, let me double check real quick. I think I don't have anything. No, I'm okay. If there are more questions, I can take them.
Okay. So we do have more questions about pricing. I remember I told you there'd be questions about pricing, because I think this is a big, question that people have, like how affordable is this going to be? So one question is like, as this is happening, does your billing update in real time, or do you only see how much it costs like the next day? And could you like set limits to be like, I don't want to spend more than $10 on this?
So that is a good question, to be honest. So the first question, is it updated in real time? I'm not sure, and I don't think so. I don't know. I'm not sure. Yeah, but I don't think it does. I think there is some kind of delay. Yeah, that's something to double check. Regarding the second question, I believe it's possible to put like a limit, but it's more like it's not specific to fine tuning. It's not specific to serverless. It's more generic Azure question on subscription. Like when you put your credit card on the subscription, I'm assuming it should be possible to put a limit, but same.
You can definitely do alerts, because I accidentally deployed way too many things on my personal account instead of my work account one day, and it was a very bad day. And I set an alert, but I don't actually know about limits. So those are great questions, because we obviously don't want people to spend more money than necessary. So another question related to that is, does AI Studio have a tool to estimate costs for deployed models? You did show the pricing in AI Studio, but I don't know if people are looking for even more detailed cost estimator than that.
No, I don't believe there is, but I believe it's rather, let me see, because when you select the model, what did I do? Okay, when you select the model, you have the pricing here. It's a simple multiplication and addition. So it would be better if we had a tool, but we don't. You have to do the calculation on your own. Also, be aware of the fact that it doesn't take into account like networking, other costs. The costs displayed here are only for like this one model. Like the cost of infrastructure, of other infrastructure pieces that you might have in your rack setup. For example, you're gonna most likely need a database, either if it's a PostgreSQL or another one, you're gonna have some additional cost, but that's to be expected. So it's a hard question, like how much is gonna cost? Oh, but don't we have like a generic like Azure cost calculator?
Yeah, we do have the Azure cost estimation calculator. I haven't tried using it for
Either have I.
tuning specifically. It definitely has, the estimation for when you're using Azure OpenAI and you put in like your number of tokens. So you can look at the Azure pricing calculator to see if it would help with that. But I don't honestly know if it has all the information from these serverless models yet. I can't remember looking that up. So those are good things that we can dig into more. Couple questions on use cases. So somebody is working with documents that have lots of internal jargons and acronyms. Would it make sense to use fine tuning for that? Or, would you do it something else like providing?
No, that's precisely what fine tuning excels at.
Okay.
Because like jargon and like very awkward domain specific terms are precisely what does not exist in public data sets. So that's precisely what large language models are going to be bad at. So for example, if you ask a public model to give you an answer using some concepts for which in your industry, in your expertise, there is a more like a different word, a different term, or an acronym, the public model is going to lack specificity and is not going to use the words of your domain. Whereas fine-tuned model, you will teach the model what those jargon and acronyms are, and it's going to use those in the answers. The only catch with that is if the jargon and acronyms are so awkward that there is no embedding vector to represent them. Like for example, imagine that you have some jargon which mixes like symbols, like I don't know, like a dollar with a weird money. I mean, I don't know, like you see what I mean? Like ASCII characters that come in a combination that is so rare that the embedding model does not have a vector for that. Theoretically, it might happen, but it is such an edge case that I don't think.
Weren't you thinking of fine-tuning embedding models? Because if you fine-tune an embedding model, then
yes,
that would.
Yes, so you can do that, but fine-tuning an embedding model is a different subject. It's more technical than fine-tuning an LLM, for the simple reason that there is no like serverless infrastructure as a service to fine-tune an embedding model. When it comes to fine-tuning an embedding model, it comes to spinning up your own GPU. I mean, even if it's on the cloud and you use like you rent the GPUs, but still you need to like spin up the GPU-enabled VMs. You need to get quota. I mean, you need to get your hands on those. Then you need to set up the whole Python fine-tuning infrastructure with PyTorch or something else. So it's level 400. Like it's a higher level of expertise. It's possible though.
Okay, great. And then one other use case, someone was asking about fine-tuning an LM to output JSON. And of course, I mentioned that we do have support for structured outputs in the Azure OpenAI, but those aren't compatible with the zero data retention policy. And whereas if you fine-tune, you can control your data retention.
So this is a good question, a very good question. So this is this is a hard problem because you know how you have usually for most models you have a code specific version. Like usually you have Llama code or whatever. That's because those models are fine-tuned on a huge quantity of code, which includes JSON documents. And when it comes like generating JSON, in my opinion, okay, good. OpenAI decided to do that. It makes developers work way easier. But I don't think if it was the most sound decision to make in the context of LLM technology, because generating JSON is actually incredibly difficult for an LLM. The way it's designed, like let's not forget that an LLM is a statistical distribution that for a sequence of tokens generates the most probable next token. So when it comes to a JSON document where it is a symmetric structure where each opening, what is the word, like the curly brace, each opening curly brace needs to be matched with a closing curly brace. This is insanely difficult from a statistical standpoint.
Mm-hmm.
So it requires a gigantic amount of information to get the model to generate valid JSON. And interestingly enough, when you look at the first, like at the original ChatGPT, it was bad at that. Like sometimes it would generate JSON, sometimes it would not, sometimes it would be invalid. Like it was bad. It's only recently that LLMs have gotten to the point where they became pretty good at generating structured outputs such as JSON or XML. But this is very hard. So I would not recommend trying to do that on your own or for your own data set. I would rather encourage you to choose a simpler type of structured document structure such as CSV or tabular tab delimited, or I don't know, any kind of non-symmetric structured data format. It's way easier.
Right. And then also, I mean, and JSON is a recursive hierarchical structure, right? So
Yes.
that also makes it.
You are right. I mean, yeah, so not only is it symmetrical, but it's hierarchical. So of course, yeah, I mean, CSV, not everything can be represented efficiently. As soon as you have recursivity, as soon as you have like nested things, you need some kind of symmetry, but still, I would encourage to go with a simpler format than JSON.
Yeah, that's really, really interesting. Okay. One more question is about chunk size and chunk overlap. And this is a question we always get when we're talking about RAG, right? And I pointed out the AI search team. They have a great blog post where they looked at optimal chunk size and overlap for AI search. But I'm curious, like what does RAFT do? Like how do they decide on the chunk size and overlap? And do they have any tools to help you?
Okay, so again, very interesting question. Thank you for asking that. So RAFT comes by default with something called a semantic chunk strategy, which it comes from they use the open source Llama. Forget if there's Llama Index or no Longchain. Sorry, they uses one of the experimental components of Longchain, which comes from a paper where instead of chunking fixed size, like fixed number of tokens, they use some kind of semantic approach to make sure that when you cut, you don't cut in the middle of a sentence. Like you try to cut when there is a dot, like at the beginning of a paragraph, at the end of a paragraph. So some kind of flexibility to avoid like losing interesting context. That being said, even then, it's not perfect. Like sometimes you might be lacking some piece of context, which is what's just before or just after. And so when you create the embedding for the chunk, it's actually irrelevant. Or you get the same vector for two different chunks, which are actually talking about two different things. Because, for example, if you take a chunk about vampires, another chunk about bats, it might, because some kind of bats are vampire bats, you might end up with like a similar vector when in fact you're talking about two different things, or vice versa. I mean, so you can have false positive or false negatives. And so it's not perfect, which is why overlap is interesting. But I must admit that right now for RAFT, there is no overlap. The chunks, so it uses semantic chunking, but it does not use overlap. And it's not currently configurable. Would it improve the situation? To be honest, I don't know. I don't know if it's relevant in the context of RAFT. It's definitely relevant in the context of RAG, because for RAG, you want to contain a bit more to avoid false positives and false negatives. But in the context of RAFT, since it's about generating questions and answers and chain of thought about a specific paragraph, I don't see how overlap would improve things. I might be wrong, but that's my without having thought too much about it, that would be my answer. I think it wouldn't help.
All right. Yeah, that's really interesting. Okay, so another question is it beneficial to use fine-tuning if your documents are in a non-English language? Would that be a good use case?
Yes, of course. And by the way, before I answer that question, just to be sure I get one thing straight, and I'm not misunderstood with what I said before. So overlap would not help with the RAFT synthetic dataset generation process, but it would help with the RAGs indexing step. Just to be crystal clear. So back to your, and here I am, I forgot the question.
Languages other than English, yeah.
Other languages. So yes, I believe it will work, but it would work exactly the same way as it would for English. What I mean by that is that there is no I believe additional benefit or less benefits for the language, maybe other than the fact that maybe large language models during pre-training there is a bias towards English language knowledge parts of the internet. So by fine-tuning and applying RAFT on different languages, yes, you might be able to fix the bias which is naturally occurring during pre-training of those large language models. So that would be part of the answer. It is not backed. What I'm saying here is based on intuition. It is not backed by data. So caveat here. But yes, I believe it would help a bit. That being said, be aware that that would not change the fact that embedding models are better for English language. So even if I believe there is work done, and I believe the latest Llama 3.1 embeddings is better, or is it a different vendor? Sorry, I might be mixing up with
the new OpenAI text embedding 3 models are better for international.
Yeah,
we talked about we talked about that at the Monday session because Anthony's done some research into that.
Okay, so those latest embeddings are better, but still you are RAFT is not going to help. It's still going to be bound by the accuracy, by how good the underlying embedding model that you use for the RAG setup is.
Yeah, and we do have, I think there are some embedding models coming out that are specific to a language too. Then that might be good to use for a vector search. I think there's ones maybe specific for Japanese or Korean. That would make sense to use because you still want to get good results during your actual RAG call, right?
Of course. RAFT, by the way, and I didn't mention that earlier, but so when it comes to machine learning in general, and when it comes to RAG specifically, you have two metrics that matter: precision and recall. Precision is when a good precision, I mean, it's an indication of how good your retrieval process is at returning documents that are relevant to answer the question. So that's precision. And, am I saying it? Geez, I'm confusing myself. Yes, no, sorry. Okay. So precision is an indication, it's an indication of how, if you are returning documents that are irrelevant to answer a question. So if you are returning too many documents and some of them are irrelevant, that's bad precision. Recall, on the contrary, is an indication of how many of the good documents, how many of the documents which you want to retrieve are actually retrieved by the retrieval process. So what you want is a high precision and high recall. But yeah, those are two different indicators. And RAFT improves precision. Why? Because recall is bound by the embedding model. And because RAFT fine-tunes the LLM that is going to generate the final answer, it has no bearings on the retrieval process. The only thing it can do is, once it looks at the documents that were retrieved using the embedding model and the vector similarity search, it can eliminate the documents that are irrelevant. So it improves precision. But in order to improve recall, you would need to improve the retrieval process and fine-tune the embedding model. Sorry for the initial confusion.
Oh, I always get them confused too.
Yeah, same. I
always have to go to that Wikipedia article that has like the precision recall graphic on it. That does. So I know we're going so long, but that does lead me to the question I was thinking is that, when we're using like Azure AI Search has this semantic ranker, which does this really nice like re-ranking of the results that comes back, and even gives them like a nice re-ranker score threshold. And then you can even like remove the things that don't fit a threshold. So you could, like, in theory, if that works, you could have results that don't include distractors. So, I'm curious if our retrieval is like perfect, do we still need RAFT?
Yes, because RAFT optimizes two things. Thank you for that question. It's actually a subtlety. That's advanced understanding of RAFT. So RAFT eliminates irrelevant documents. That's one way it optimizes precision. But also because it learns using chain of thought to get straight to the point. Remember how I was showing that it was like returning exactly the two words or one word, which is like straight the answer. So it not only does it train the model to ignore irrelevant documents, but it also trains the model to, inside a given document, to which paragraph and which sentences and which words of the documents are actually the most relevant to answer the question. So it's however good, whatever you do during retrieval, RAFT is gonna improve the precision of your setup. And let's not forget that so fusion and semantic ranking that you mentioned, it does improve the setup, but it does not improve the semantic, the initial vector similarity search. It comes after. It's between it's after vector similarity search, and it's before context augmented generation. So it takes the list of results and which contains relevant and irrelevant documents, and puts the relevant documents at the top. So yes, it improves precision, but it does not improve recall, because if some documents would actually be relevant, you want them, but they are not retrieved because from a vector similarity search standpoint, they are too far away from the embedding of your question. They are not going to be inside the list that AI search is going to semantically re-rank. So while I highly recommend to use AI search re-ranking because it does improve the efficiency of your setup, each one of those optimizations improves the situation, but there is no single silver bullet. Like you need to accumulate the optimization and the improvement at every step of the way to improve your RAG setup as a whole.
That does lead to the final question, and we'll call it after this. But how do you then choose the best vector database? How do you evaluate that for your RAG setup?
Okay. Well, that's a tough question. you have many dimensions to that answer. There is the cost, there is the performance, the scalability, depending on what is the volume, like how much data are we talking about. Then there is the quality, like what state-of-the-art AI features does it have? Like, does it have re-ranking like AI search has? Does it have like chunk over, I forget the name, but overlap? I mean, each one of those features. So we are, like I said earlier, we are at the beginning of the AI stage, and we are still at the stage where each one of those vendors, I mean, they're state of the art, and they are pretty much all trying to implement the same state of the art optimizations that come from the papers that are publicly published and available. But still, they are still rushing to get those features in, and so we're still at the point where it's not like widely available, so and evenly available. So I would say that two ways: either you rely on third-party expertise, like third-party comparisons, or you have the expertise and the will to take the time to look at every single one of them and see exactly what are the optimizations that they implement. What I know is that AI search is interesting from the standpoint of those big AI optimizations that are where you get a lot for the buck, such as re-ranking and hybrid search. Yeah, hybrid search, by the way, too, is another way to improve recall this time. Hybrid search does improve recall because in addition to doing vector similarity search, which is based purely on the quality of the embedding model, it adds token-based retrieval, which is the old style, like before AI, when we had only full text search databases such as Lucene, Elasticsearch, that kind of stuff. Those at the time were using only token-based indexing and search. And what's interesting with token-based search is that they will return complementary results, where embedding vector similarity search is going to return both a document talking about vampire bats and bats, because in the embedding space, those two concepts are going to talk about the same thing. Or if you talk about Dracula, like Dracula and vampire are going to be close in the embedding space. Whereas with a token-based approach, if you were searching for vampires, it would not return documents talking only about Dracula. It would not. But if you search for like IDs, like technical terms, like for example, a reference, like if you have a catalog of products or like car parts, where you have like sequences of characters that make no sense to a human, like X, Y, 0, 2, 3, B, Y, Z, whatever. That sequence of characters makes no sense from a language standpoint. So in the embedding space, you will not have a good vector for that. But from a token standpoint, using old style full text search, if you search for that keyword, it's going to return all the documents that contain them. And so it's going to improve recall for those situations where you want to look for that kind of technical terms.
All right, this was great. We should wrap up now. Is there anything else you wanted to share in terms of links?
Just I mean the link to maybe in case anybody missed it, the link to the repository. Maybe also a blog post that I wrote where I go over those concepts. So the link is RAFT recipe blog datagen. This is a link that I can put in the chat. So an article where I go over some of the concepts that I have presented today and explanations. And there is an older blog post, RAFT blog, which was more high level, but which is also which might also be interesting. And yeah, I'm encouraged to go to the repository, clone it, and if you find issues, please feel free to submit bugs. I will try to do my best to fix them, and I already have one to fix. So
sweet. And we'll also put all these links in the GitHub discussion thread for this session, which is on the aka.ms/raghack, and we'll post that GitHub discussion thread link also in the chat. So that if you do have any follow-up questions, because there's so many questions, I don't even know if we made it to all of them. So if you are watching this now or you're watching this later and you do have follow-up questions, you can go to that discussion thread on the RAGHAC forum and ask additional questions, and we will pick Cedric's brain some more. Sweet. All right. Thank you so much, Cedric. That was super interesting.
Yeah, and thank you for inviting me. It was a pleasure.
All right. Thank you both, Pamela and Cedric, for an excellent session. We really appreciate it. And thank you all for joining today. We would love to hear your feedback. So please take a look at the survey link. The event code for today's session is 23342. And we appreciate you. We will see you on the next episode.
Hey everyone, hope you enjoyed today's session.
If you aren't registered yet for RAGHAC, you can register now at aka.ms/raghack/register, and you can introduce yourself on our forum. You can start hacking either by looking at one of our code samples or just starting from scratch. If you have any questions along the way, feel free to post them in our GitHub discussion forum, and you can also attend live office hours in our Discord. Once your project is ready, make sure to submit it before September 16th at 11:59 p.m. PT to be eligible for our cash prizes. And of course, make sure to join our upcoming live streams to learn more about RAG. Thanks for joining.